In this presentation, we will overview different network topologies and redundancy technologies. Probably the most simple topology is a bus or linear topology. Network backbone is formed by switches or other network devices that are connected one-to-one consequently. This topology requires the least amount of cables, but the flip side is low bandwidth, since all hosts utilize same backbone for communication. Also, bus topology lacks redundancy. You can imagine that if one switch goes down, the rest of the network behind it will become unavailable. Almost all switches in this topology are a single point of failure. Tree and star topologies give us more flexibility in network planning and provide with more bandwidth. However, there are still single points of failure that exist. If we keep adding additional redundant links, we will get a mesh topology. Additional cable investment gives us a higher reliability and performance. However, such mesh topologies are complicated and thus the recovery will be quite slow. The best recovery time could be achieved in a ring topology. It has redundancy capability and simplicity at the same time. The disadvantage is still low bandwidth because a ring is kind of a looped bus topology. Before we start talking about redundancy technologies, let's take a look at an issue called looping. Imagine that we have physically looped topology based on layer 2 switches, for example a ring. As you now know, every host will generate broadcast frames, ARP requests for example. These broadcast frames will flood to all ports according to Ethernet switch behavior, which means that they will be duplicated and circle both clockwise and counterclockwise. These frames will constantly change the MAC table of each switch and lead to incorrect forwarding decisions. Once the network has such troubles, the host will send even more broadcast frames because it has no correct reply. Finally, the whole network will be occupied by broadcast traffic, and the forwarding mechanism will be totally out of order. Back in the days, it was a huge problem. One engineer could bring down the whole network by plugging cable into a wrong port. This is why people started to develop redundancy protocols. The idea is quite simple. Redundancy protocol will block some of redundant path to prevent the network from looping. There are several open standard redundancy protocols like STP, RSTP, and MSTP, and a number of proprietary technologies developed by networking vendors. Moxa's proprietary technologies are called Turbo Ring and Turbo Chain. All of Moxa's managed switches support the mentioned open protocols and proprietary ones. STP stands for Spanning Tree Protocol. It is defined by the 802.1d standard, and it is one of the first redundancy protocols. STP is capable of analyzing a network topology and block redundant paths to prevent looping. The algorithm is quite sophisticated because it has to support any kind of topology. Setup is complicated too. You have to set priorities to each switch and each link to achieve the optimal performance. And the biggest disadvantage, especially for critical industrial applications, is slow recovery time. The recovery depends on the quantity of switches and can take 30 seconds or more. The evolution of STP is RSTP, which is short for Rapid Spanning Tree Protocol. The algorithm was optimized so that RSTP can recover quicker. Typical recovery time is around 5 seconds, but it can be slower or faster depending on topology complexity. The configuration of RSTP is similar to STP. In industrial applications, network failure may have catastrophic consequences, with big financial loss, equipment damage, or even human injuries. This is why it's so important to have a redundant and very quick network recovery in cases of link failure or equipment failure. To meet these high requirements, we recommend the use of simple topologies combined with Moxa's proprietary turbo ring and turbo chain technologies. Let's go through turbo ring version 2 behavior. Version 1 is rarely used nowadays because it has slower recovery. As I mentioned before, turbo ring is based on ring topology. It means that we need to take several managed Moxa switches, enable turbo ring on each of them, and connect them into a physical ring with copper or fiber cables. Among those switches, there will be one ring master. This role may be assigned manually by user or automatically based on MAC address. Even if you made a wrong setting and tried to put two masters in one ring or your master went down, turbo ring will use a special mechanism to elect only one master. It is the ring master switch that will block its second ring port and form a backup path. This way, a physical ring turns into logical bus topology. Here is a hint for you. Wise master switch placement choices allow you to optimize bandwidth usage. If a failure happens, the backup path will be activated immediately to allow further network operation. For a single fast ring Ethernet that consists of 250 switches, recovery will take less than 20 milliseconds. In case of a gigabit ring, recovery time is less than 50 milliseconds. Such tremendous recovery speed for large-scale networks is the key value of turbo ring technology. To provide flexibility, turbo ring version 2 supports additional features for redundant ring interconnectivity. They are called ring coupling, dual homing, and dual ring. Let's take a look at some typical application scenarios. In case of both rings are located in a harsh environment, we recommend the use of ring coupling. Ring coupling utilizes two switches from each ring to create a redundant interconnection. You can see primary coupler and backup coupler. If one of the rings is located in a normal environment, we could save some money and use dual homing. For this case, both interconnection links are coming to one switch on the normal environment side. That switch is a single point of failure. However, it is reliable enough in a non-harsh environment. When both rings are located in a non-harsh environment, we can lower down the cost even more and use dual ring. Here we have one switch that belongs to two rings at the same time. Please remember that one switch can be a part of only two rings maximum. Turbo chain technology is a logical evolution of turbo ring, which is based on bus topology. We recommend the use of turbo ring for a backbone network and use turbo chain to expand the access layer. Turbo chain is an independently redundant part of the network. You can attach new chains without interrupting the operation of the rest of the network. Here is a turbo chain idea. We got three roles: head, member, and tail. These roles can be set via management interface, such as web console and CLI, or by dip switches. Tail will block its tail port and form a backup path to our backbone network. If a failure is detected, the backup path will be activated. Good news is that turbo chain can be attached not only to turbo ring, but also to any other type of third-party network. Recovery time of turbo chain itself is similar to turbo ring. Less than 20 milliseconds for fast Ethernet chain made of 250 switches and less than 50 milliseconds for gigabit Ethernet chain. With turbo ring and turbo chain technology, you can easily build reliable industrial networks. Here are some real cases examples. This diagram is for gas pipeline, As you can see, the backbone is made with turbo ring technology and remote areas are connected with turbo chain. In a wind farm application, typically every tower is connected to a control center. But tower location patterns don't allow the use of single ring backbone. For such applications, turbo chain is an optimal solution. Please pay attention to how head and tail placement alters from chain to chain. This is done to optimize load balancing. Here is one more example from a railway field. Despite the fact that stations are located in one line, we can still use a turbo ring connecting next but one station. Also, in this example, you can see how turbo chain can be used to create a multi-layer topology. Now that you know the basics of redundancy technologies, let me show you some nuances that you might encounter. You can use different kinds of media within one ring and also different link speeds. However, please remember that overall recovery time will follow the worst value of all links. It means that if you have a ring made of fast Ethernet links and at least 1 gigabit link, the recovery time would be less than 50 milliseconds. Another common question is, can I use a media converter in a ring? From the first look, you may assume that media converter is a layer 1 device and should have no impact on turbo ring operation. However, it's not that simple. The reason is that turbo ring's fault detection is based on link status. In case when the fiber link is broken between two media converters, turbo ring switches will not detect that failure because both copper ports are still active. To prevent this confusion, you can use a media converters with link fault pass-through function. This will shut down copper ports in case of fiber failure and vice versa. However, this process also takes time, so we cannot guarantee recovery time for such topologies. So our general recommendation is not to use media converters in a turbo ring or chain. Another frequently asked question is, can I put unmanaged switches in a turbo ring or chain? The answer is no. Because according to the recovery mechanism, after backup path is activated, all switches have to flush their MAC table, so the forwarding logic will be reset, and frames can travel along a new path. An unmanaged switch cannot flush a MAC table by command, so the recovery time will be limited by aging timer of that switch, which is typically several seconds. We have created several video clips to introduce turbo ring and turbo chain technologies and uploaded them on YouTube. Please take time to check it and feel free to use it in your daily job to introduce technologies to customers.